Are we going to baseball too? Is it new? That's my next second. I think it's new. Ja. Nee, man hat
I'll hop back and forth.
Okay. I guess I'll get started now. So last time I talked about this idea of surrogate losses, which is one way we can motivate the use of support vector machines and logistic regression. And it sort of indicated that the least squares loss was not really an appropriate loss for classification. So this time, but all of that was within the context of linear separators, right? So everything was linear in that case. So this was sort of the simulation that I was using as an example. The red and the blue dots here are pretty well separated by a line, and that's actually the optimal separator for this, for the generating mechanism for this data set, is linear. And it's one big innovation was the ability to go from linear to nonlinear through the use of kernels, which is mostly what we're going to talk about today. But along the way, we'll talk about a little bit about overfitting and underfitting because it becomes relevant. Okay. So I've constructed a data set. And this is just sort of this is a simulation, and the idea is that there's some sort of polynomial equation here in these two variables that can separate out these two data sets, so the red and the blue. I'm not telling you what it is. Maybe if I was extremely generous, I would tell you perhaps the degree of the polynomial. So there's some polynomial for which if it's positive, then we have reds, and for which if it's negative, we have blues. So this is generalizing the idea of linear separators, right? Because linear separators says if there's a linear equation, if that linear equation is positive, then it's red, or it's expected to be red, or red is your best guess, and then if it's negative, then blue is your best guess. So this is one generalization of the idea of linear separators is through polynomials, right? Polynomial separators. And by polynomials in two variables, right? We have two variables that includes cross terms, x1 times x2, and so on. Okay, so suppose when you get a data set, right? We're doing simulations, and so we can visualize it very easily because we've constructed it to make it visualizable. There's really no, the only noise that's entered in here is how the x's are sampled. Right? All of the y's are just determined by whether or not they're above or below the decision boundary here. So there's very little noise in this data set. Really, the challenge is going to be coming up with an exotic enough class of possible separators so that we can encompass this polynomial that actually separates it. So really the problem right now is sort of an issue of overfitting. If we were to use a linear separator on this data set, so we just plug it into linear or logistic regression, right? There's no real noise in the y's, But the issue is that when we, so this is predictions, the predicted labels that come out of a logistic regression fit on this. The issue, of course, is that you can't well represent that polynomial using just a line. And so you'll get quite a bit of error from this. And so if we look at our confusion matrix for this linear fit, remember the confusion matrix, it was just comparing the number of true positives, false positives, true negatives, and false negatives. If we look at the confusion matrix, there's quite a few errors. So we have, if the predicted label is positive and it's a false positive, there's 116 of those. And I sampled 1,000 of these, so that's 10%, over 10%, 11, 12% of them are false positives, and then almost 10% are false negatives. So this is doing quite poorly. Right? The proportion of correctly labeled data points is something like 80%. So they're doing quite poorly, and of course it's because there isn't a good linear separator for this data set. So of course, again, I want to emphasize that this is a simulation. It's only for demonstration purposes. If you have a real data set, oftentimes it's pretty hard to visualize the data, so you wouldn't even notice that it wasn't linear or it was linear. You would just run logistic regression. You would hope that it worked out. You would see these numbers, and you might not know whether it's because you haven't built a flexible enough classifier, or it might just be because this is actually the best you can do. This might just be the optimal error, and there's some sort of irreducible error that you can't overcome. So that's the main complication, is that in reality you don't know that there's some polynomial separator. So part of this, what we do typically is we think of all of the situations in which we might be able to change our classifiers, modify our classifiers, and then suddenly start to do quite well. Right? So polynomials, polynomial basis expansions, this is one way that if the data just happens to look like what the simulation is telling us, then we actually can do quite well. Okay, so where are we? So I'm going to change so what I'm going to do is I'm going to make transformations of these x and y variables. So let's look back up at this plot. Or I should say x1 and x2. Y is going to be thought of as either positive or negative. So I'm going to make a transformation of x1, x2, and I can combine x1, x2 however I like. Really, I have complete freedom in this. But the idea is that this transformation, I'm going to design it so that the transformation actually gives me more features. So this is something that people are accustomed to. It's called feature engineering. It's this idea that from just a couple of features, you can build many features by combining them somehow, making transformations, and so on. So we're going to create the polynomial features, which, again, just remember that we do not know that this, in reality, we won't know that this separator is polynomial in nature. So it's sort of like, if I was able to guess that, then I could build these features and do this. In reality, this is not exactly realistic. But just suppose that we did know that it was a polynomial boundary, and it actually turns out to be quadratic in this case. So what I'm going to do is I'm going to build the features. So I'm going to keep the intercept, so the 1's feature, the x1, x2, but then I'm going to add in x1 squared, x2 squared, and x1 times x2. So actually now I have 6 features. And before I only had 3. I had the intercept, and then x1 and x2. But then I add those three quadratic monomials. And then what I'm going to do is take a linear combination of those. And this is sort of, because I know what the true separation boundary, I'm going to opportunistically combine those features somehow. and then plot two different ways of combining those features. So one way is taking minus 0.2 times x1 squared plus 8 times x1 times x2. And that's what this is. The x-axis of this plot. The y-axis of this plot is minus 0.8 times x2 squared minus 1 times x1 minus 0.5 times x2. And so that's another just linear combination of those features that we constructed. So you should think of what we're visualizing here is a two-dimensional subspace of this six-dimensional space, right? Because we've taken a linear combination of some of the features and then another linear combination of the other features. So this should create a two-dimensional subspace. And it turns out that if you project all the points onto this, so you only think about what these two values are for this two-dimensional subspace for all of the points, then it turns out that if you look at it in this space, then you get that you have this linear separator. Yeah.
So are all these coefficients chosen arbitrarily?
No, so these are very strategically chosen, and this is only possible because I know exactly how the data is created. Right? But you don't. The only reason I put this up there here is for visualization purposes, right? So if when you project onto a two-dimensional subspace, and if you have a linear separator there, then you can also find a linear separator in the full space. So that's sort of that's just sort of a fact. So anyway, so this is just the only reason I plot it like this is so that we can visualize it. It can make sense. But in reality, we have this larger six-dimensional space, and it turns out that there's a linear separator in the six-dimensional space. And so it's sort of like what happened here was that, you know, I knew for some reason or another that there was a good separator in this six-dimensional space. I didn't know exactly what the separator was, so I just projected it onto this. I expanded the basis, made three features into six features, and then I can perform logistic regression on this. So here's the idea of this embedding. So we have x1 and x2, and we create these six features: 1, x1, x2, x1 times x2, x1 squared, x2 squared, and then it turns out that the optimal classifier, I can completely separate these two with the following data vector. And this is where I got those numbers when I took that linear combination. So this is how the data was generated. I created random x's, and then I just created my y's according to this linear combination. And you know, you'll have to. There's some abuse of notation. I'm just saying y is equal to true or false. True if this is true, or false if this is not true. You know, we were using red and blue as our labels before. We could use 1 or 0. So that I'm abusing notation a little bit here. So I can fit the logistic regression in this with these six features. Right? I created six features. I have them. I have my y's, I have my reds and blues. So I can do that. And then I can get the so when I do this, I can construct our confusion matrix, and we get near perfect separation. And this additional error is just a numerical instability. It really shouldn't be perfect separation, because there is a perfect separator here. So you know, this of course, that should say polynomial fit, not linear fit, in confusion matrix. So the idea was that, you know, is that, okay, actually I think okay. So yeah, so we got a pretty much a perfect classifier out of this idea that we create more features, and then we use our usual linear methods with these more features. Is there a question? Yeah.
I was wondering, can you use principal component analysis to like figure out how, like, to get that linear?
Yeah. So this is a lot like PCA. But the big difference is that, you know, so when I expanded into the large basis, right? Really, what ends up happening is that you get this curved, this two-dimensional curve in this manifold in the six-dimensional space. So it's not going to be a linear subspace that everything lies close to. So if you were to do PCA, you probably would lose a lot of the, you would lose the shape of the curve. Yeah. Really, we're learning this line using the Y's. That's the big difference between this and PCA. PCA doesn't use the labels themselves. So PCA shouldn't work in this context, and it's because it's not supervised. Yeah, and that's a good question. So yeah, okay. Where am I? Okay, so I'm gonna do some math now. So, beware. Switch over. Okay, so one way that we can write this is, first of all, we start with our xi, and let's say this was two-dimensional features. It's a feature vector. So we had our two-dimensional feature vector. This is our first and second dimensions here. Now what we can do is we have this way of turning these two-dimensional features into these six features, if you include the intersection. And so we'll call this phi. Phi sub L of xi. This is the Lth feature in this high-dimensional embedding. We're going to call these things high-dimensional embeddings. So this is quite general. So in our example, for example, phi1 of xi, this is just equal to 1. That was the intercept. Phi2 of xi, this is equal to xi1. This is the first component of x. And then we have phi3 of xi. This is equal to xi2. And then we have phi4 of xi. This is equal to, now we start getting the nonlinear part. Right, so we get the x1 squared, phi5 of xi. This is equal to our x1i times xi2. And then we have the phi6 of xi. This is equal to xi2 squared. Okay. So this is just another way of writing this expansion into more features. We call it a high-dimensional embedding. Okay, so really the way that we all think about this is we just create new features, right? It's very intuitive, and it's sort of a very common practice to just construct features out of your existing features, and usually you use some sort of domain knowledge when you do it. Industries have their own features that they like. Insurance industries have specific features based on age and credit history and the number of claims that you use and things like that. So the number of claims that you have on your insurance policy and so on. So every industry tends to have their own ways of engineering features. So this is quite general, and it's very natural to construct new features and then just apply your favorite method to those constructed features. So, so the way that we're going to think about it then is that zi is now just equal to phi of xi, or phi is now thought of as a vector. So z is a vector, but now it's in 6 dimensions instead of. So this is now our 6-dimensional engineered feature vector. I'll just call it features. No. Okay. And then we just do all of the usual things within this. And then the power, of course, is that we have all of the technology to construct linear separators. Why not use them in this context? Right? All right. So, for example, support vector machines. SVMs, they were based on this hinge loss, right? So, yeah, if you remember from last time, the SVM procedure was you minimize beta within your, this is a p-dimensional vector. You minimize beta for this 1 over n, sum I equals 1 to n, of, now what we do is we have this 1 minus yi, and then we have the sum over j equals 1 to p of zij times beta j. Positive part plus lambda times beta sum I equals 1, j equals 1 to p of beta j squared. Okay, so what's going on here? So first of all, this is the form for support vector machines if yi is within 1 or minus 1, first of all. So it's assuming a certain encoding for the y's, right? We in the pictures we have blue and red. I'm just going to call one of those 1, one of those minus 1. The red's the 1s, the blue's minus 1. You know, if we're talking about positive and negatives, then I'm going to encode the 0 as a minus 1. And I'm only doing this to make the math easier to work with. So it turns out that the hinge loss is always this thing. It's always this 1 minus yi, and then times our score. And our score was the weighted sum of the features. So this is the weighting by beta, right? Beta j times feature j, and those things summed up. And then it's this positive part of this vector, right? Because we have that this hinge loss. We have the hinge loss look like the following. If this is yi times this score, si, this is our score for I, right? This is our learned score for a certain beta. And then we just write our hinge loss as a function of this. Remember, it came down linearly until it hit 1, and then it was 0. So this is our hinge loss. Now, I didn't talk too much about the full program that we solve to get the support vector machines, but we also tend to add this. This is called a ridge penalty. And the idea is that if you have perfectly separable data, then what ends up happening is that there's an infinite number of betas for which this loss is 0. So we have to have some way of selecting an appropriate beta. And so what we do is we add this ridge regularization term. This lambda times the sum over the j's of beta j squared. So there's a lot of ways that we can think about this, but for now we'll just say that this makes it so that we have a unique a unique solution. And it also makes the problem a little more numerically stable to add this in. Okay, yeah, and this positive part is just, it's just 1 if this thing is positive and 0 otherwise. So here, so when I write something like m positive, that's just equal to m if m is greater than or equal to 0, and 0 if m is less than 0. So you can verify that this loss is exactly what I drew here. This line, yeah.
So, is there any reason that you prefer this form of penalization to other forms like the form of data or other?
Yeah, so this form of penalization has a couple of advantages, first of all. One is that just numerically, it's nice to work with the sum of squares. It's differentiable, it's being quadratic. If you did say the sum of the absolute values, like you suggest, then it has this disadvantage that it's non-differentiable, and it'll also have this tendency to force some beta j's to be 0, which you may or may not want that. That's sort of that's like a lasso type penalty, and that's that could be advantageous for sure. If we were to make it an all-one penalty, this would turn out to have an equivalent form as a linear program. This would be a linear program, which is a whole other can of worms, optimization-wise. So anyway, I'm sort of remembering what notation I did and did not introduce last time, and so bear with me if I haven't introduced something where some notation or algebra is tough. Then just tell me and I'll explain. Okay. Okay, so this is the support vector machines objective. Yeah, sure.
So there 1 minus yi times si is what you have done here, right?
Yeah, so if we draw it as though this plus, so this is the positive part of this as a number, right? This is a scalar.
Right.
So if the yi times this si is very positive, then this 1 minus it is going to be negative. And so that's going to be 0. And so that's why we have a 0 for that being large. And then if it drops below 1, then this is going to start to be positive, and it's going to have slope 1 as we decrease. So, or slope minus 1 as we increase. So that's the idea. So that's what we're seeing here. And then we add in the sum of squares. So this is what the typical support vector machines, the regularized form of support vector machines. Okay. Now, there's last time we talked about writing everything in terms of this score, right? The logistic regression loss, it was also in terms of the score. And same with the least squares penalty. So we could write these. So we could also use other losses. Other losses. And they would take the same form where we minimize over beta. Now this 1 over n sum I equals 1 to n, this is the average of the losses, which we call the empirical risk. And this loss we can just write as a function of yi and then zi transpose beta, where zi transpose beta is exactly this sum. So if you take one vector, transpose another, you're just summing the components multiplied by each other. So we could use the other losses in this context, and they would all they would be able to be written in this way. And then if we were to add in the same penalty, if we were to add in the same penalty, which we call this ridge type penalty, which will have the effect of making the optimization a bit more stable. Maybe we'll have time to talk a little bit about the effect of this ridge penalty. Typically, it's not that the addition of it is not that serious. Most of the time, it's used for numerical purposes. But so we could use other losses, and they all take the following this form. Okay. So now, one of the questions is, what happens when we create a lot of features, a whole lot of features, more features perhaps even than the number of samples? Then it turns out that this is actually, you could actually write the solution to this in a way that the complexity, the computational complexity, scales only with n. It's not scale with p. And this is what the kernel trick is. So we'll talk a little bit about this, but it also has other implications in terms of designing features, that we can actually bypass designing features entirely and just design kernels instead. Okay, so this is the basic form for our minimization. And this loss could be the logistic loss, it could be the SVM loss, and it could be least squares loss. Even though least squares, we talked about its disadvantages, everything follows, even if we use that. Okay. So we're gonna derive the kernel trick here. So what I'm going to do is I'm going to think of beta in the following way. So first of all, for any vector, so beta is a vector. It's a vector in p dimensions, whatever p is. So actually are the ZIs. Right? The ZIs are also, this is beta, this is Z1, maybe we have Z2 here, and so on, up to Zn. So we could think of beta as being, having some part of itself, which is a linear combination of the ZIs. Because they're all vectors in p dimensions. So I'm going to write beta as a sum over I, alpha I, Zi, plus some other term, which I'm just going to call beta sub, I'm going to put this little perpendicular sign. It's upside down t. Now, it turns out, and this is a fact from linear algebra, it turns out that you can always write a vector as either as the sum of something that's a linear combination of other vectors plus another vector which is orthogonal to all of those vectors. And so we can always write beta in this way for some alpha 1 to alpha n being real numbers. These are real numbers. And then beta orthogonal such that when you take the inner product between it and Zi, then it's orthogonal to all of these. Right? So the image you should have in your mind is that there's some beta orthogonal such that beta can be written as this linear combination of the z's, where this beta orthogonal takes a right angle to all of these z's. So this is the most linear algebra intensive part, I think, of this whole thing. So bear with me. It's important in machine learning to have a good intuitive grasp of linear algebra. I think most, and so so we're gonna try to do this as intuitively as possible. But I don't think you can get around the use of linear algebra if you want to have a good understanding of the kernel trick. But this is the basic property, that we can write beta as some linear combination of the zi's plus some other part, which is orthogonal to all of the zi's. Right? It takes a right angle to all of the zi's. Okay. Now,
Quick question.
yeah, go ahead.
The last term that you wrote there, the inner product of
Oops, sorry,
I
I didn't finish that thought.
is equal to 0.
Yeah, that's equal to 0. Thanks. Yeah, I have some pretty intensive ADHD, so sometimes I'll just lose something, right? So,
So you mean if I visualize beta as in this space, in this plane, and if beta perpendicular is like this, then beta would be something.
Yeah. So there's, so maybe, so the idea is that I'm entertaining, okay, so maybe if I draw it in 3 dimensions, if I can, then it'd be easier. So, so we have the z, maybe this is z1, maybe we have z2, and we're thinking of all of these z's perhaps on the plane, the xy plane. And then I'm entertaining the possibility that there's some beta orthogonal, which is orthogonal to all of these z's. And then beta will be something that's some linear combination of these. I'm actually going to demonstrate that beta orthogonal, this beta perp, is actually 0 for the minimizer of this perp. So that's where we're going. But right now we're entertaining the possibility that there's some part of beta that takes a right angle to all of the samples. So we'll entertain that possibility. Okay. So now, yeah, go ahead.
So a linear projection or regression tells us that there exists a beta that's orthogonal to the sum of alpha I, z I, right? And always. And on top of this, you add a new condition that it's orthogonal to each component individually, or am I getting confused?
It's now you should think of it. So actually, in linear regression, a lot of the times when people explain linear regression, multivariate linear regression, is that you're actually projecting your y's onto this span of the columns of x. This is actually sort of the opposite. We're now, instead of thinking of the space of the features, we're thinking of the space of the samples themselves, right? So this is in p dimensions, and now we're thinking about beta as being some linear combination of these p-dimensional vectors, which are the samples, and then the orthogonal component. So it's
My question was like, my understanding was that like the beta remainder would be orthogonal in the first equation to the sum of alpha I, z I. Always.
Yes.
And now you wrote actually was also orthogonal to each component.
Oh, right. So that's right. So what you said is true, but it's not sufficient for what I want. What I want is that it's orthogonal to all of the ZIs.
To each of them.
To each and every one.
Okay, and that's not, I mean, the first property is always verified and the second is not always verified, is that right?
So this beta can always be written in this way. So think about it like you start with a beta, and then you remove the component that's that can be written as just some multiple of z1, and And then you remove the part that can be written as a multiple of Z1 and Z2, plus C, multiple of Z2, so in the span of those two vectors. Right? And then you remove the part that's in the span of the first three, so on. And you keep doing this, and what's left over is this remainder beta perfect. Yeah, does that make sense? Yeah, okay. So that's a sort of algorithm that proves that this exists, the existence of this beta perfect. But it happens to be orthogonal to all of the ZI. So you could also write it as, for a given set of alphas, you could write B perp as perpendicular to that sum. Right? But there's more information here in the set it's orthogonal, every single one. This is good. This is like, I think this is good to get our hands on, to get our heads around, because yeah. So now let's look at this loss. Right? This loss has the ZI transpose beta in it. That's how beta appears in the loss. If we look at the ZI transpose beta, well, this is just equal to the sum over I, alpha I. Oops, I should write ZJ transpose beta because I'm using the sum over. Actually, let's keep this I and make this J the sum. J. Oh no, I'm using J for that. Let's make it sum over K then. All right, eventually I'll get there. I'll use K for something else later, but hopefully the context will be clear. Okay, so we have ZI transpose ZK plus our ZI transpose beta perp. So I just plugged in the definition of beta here in the ZI transpose beta. I'm taking the inner product between ZI and beta. And I can just distribute this over the sum, right? So I get the sum over the alpha k's of ZI transpose ZK, or VK. And then I have this ZI transpose beta perpendicular, so this inner product between things. But we already know that this is equal to 0. This is by construction. Okay. So now what do we have? We have that beta, or sorry, the ZI transpose beta can be written just as a function of the alphas. Right? That's one thing. So we have that the minimum. So now the SVM procedure, let's call it star. Star here is this minimizer. Now, since I wrote beta as this, based on these alphas and this beta perpendicular, I'm just going to make it so that we're trying to minimize over the selection of alphas in this beta perpendicular. Because these two things give me beta, so I'm just going to say it's minimized with respect to these two. And now I have my 1 over n, sum I equals 1 to n. So my empirical risk, L, yi. Now I have my ZI transpose beta, but that was the sum over k of alpha k times ZI transpose ZK. Okay. And then I have plus lambda, sum j equals 1 to p, and now I have my beta j, but that's equal to, I can write that the sum over k, alpha k, z I j, plus beta perpendicular, so j squared. So I just took the objective that we have above, and just plugged in what we have here, this zij, and then this is just the j component of beta from this. Okay. So yeah. So bear with me. There's a bit more math to come, but we'll get to a very nice spot at the end. I can convince you of that. Okay, so so the first thing is that the beta perpendicular does not enter into this empirical risk part, right? It has no influence on this at all, the loss. It only has an influence on this. Okay. So let's expand out this thing. Let's call this, I'm going to call this R in parentheses. So if I write R in parentheses here, then I'm just expanding out this thing, this whole thing. So this is lambda. Now we have the sum over the j's. And then we are going to square this, but I'm just going to do it by saying, let's just expand out this. This is the sum over k, alpha k z. Oops, I'm sorry. I'm using I there. Should be kj. Zkj. This whole thing squared plus our 2 beta perpendicular j. Now we have a sum over k, alpha k, zkj. And then we have whatever's left. So this, it's not the sum now, it's just the beta per j squared. Okay. So now let's use what we know about. So let's focus on this term. So I'm going to call this C in parentheses, and I'm also going to keep this sum here because this sum over j is important. The C, this is equal to, we still have this lambda term, sum over j, sum over k. There's a 2. Let's bring the 2 out in the front. And we have alpha k, beta per j, z k j. So we have this. Okay, so now this is starting to look like an inner product between the beta perpendicular and the zk. Right? We can switch the sum over the j and the k. We can now sum first over j and then over k. So let's do that. This is 2 lambda sum over k. And then we have the alpha k can come out, sum over j, beta perpendicular j, z kj. Okay, so now all I did is I just switched how I was doing this sum here. And now I'm just going, because really what I want to get out of this is this inner product between z perpendicular and z. Yeah, that's right. So this part right here is this beta perpendicular transpose z k, and that's equal to 0 by construction of this beta perpendicular. Okay. So I've shown that this cross term is 0. So now if we were to put this all together, we would see that the regularizer term, this lambda sum of the beta j squareds, it can be written as something, lambda times the sum of something that has nothing to do with beta perp, and then just lambda times the sum over j, this beta perpendicular j squared. And that's the only place where beta perp comes in. So I'm just going to say star is minimized over our selection of alpha and beta perpendicular something. So I'm just going to put the ellipses there. That's only dependent on the alphas, not on the beta perp, plus our lambda sum over j, beta perp j. Okay. So now this was a lot of work, but now we have our conclusion, which says that if we want to minimize this over the selection of beta perpendicular, it doesn't matter what alpha is. This is going to always be 0 for the solution. So the beta perp is equal to 0 for any minimizer. Because you can never you can never make the, because the sum of squares is always greater than or equal to 0, so you might as well set it equal to 0. So if you wanted to minimize this, you would just always set this beta curve equal to 0. So this is sort of a magical thing, because what we've done is, under this relatively general form, where are we, for this loss here, right? So this could take the logistic loss, the support vector machine loss, the L2 loss. Under this pretty general form, the beta can be written as a linear combination of the samples, right? The solution. So when we actually do the optimization, we could just forget about beta being anywhere outside of that. So this is the kernel trick, and we'll introduce why it's called the kernel trick in a second, because there's kernels, this idea of a kernel involved.
So if you just go to the end of what you do, so what is the point here? That you express when you added that regularization term, you added beta, and then now you're saying that if you initialize or assign beta perpendicular to 0, that's what is going to give you the minimum value for this equation.
Yes. So now the idea is that we had something that was a program in p variables, right? The beta had p variables. Now we've turned it into something where we're minimizing over alpha. I'll just write it out. Sum I equals 1 to n is loss yi, and now the zi transpose beta was written as a sum over k, alpha k, zi transpose zk. This is the loss term, plus now lambda, we have our sum over j, sum over k, alpha k, z, k, j, this whole thing squared. Okay. Now, what this says in the high level, first of all, this alpha is in Rn. So what this says is that P can be, if P is much larger than N, right, we've constructed way more features than samples. Then it turns out that we can write our program as something that's just in Rn instead of our P. So we can select the smaller of the two, N or P. We could solve the problem either in RP, just P variables, or in Rn, depending on which is easier. So that's one sort of algorithmic implication. But another thing is that actually let me jump to this notebook and see what I have here. Okay. I'll finish talking about kernels. Okay. So let's remember what these z's were. So we have the zi transpose zk. Okay, in here. All right. So this was phi of xi. This is the vector. We can transpose it with phi of xk. That's what we have here. So now what we're going to do is we're going to think of this thing right here as a function of xi and xk. Right? So if you gave me two samples, then I could spit it out. And we're just going to call it k of xi, and this is where I'm going to regret having used k, as an index. I'll use capital K, or maybe I'll use a kappa. Let's use a kappa. Typically, it's a lowercase k is used there, but I'll just use kappa. So we'll just call it this, right? Because if I told you what this is, say it was that polynomial basis that I used before, then then I can figure out what, analytically, I can figure out what this inner product would be for any x1, xi, and xk. Right? And so I can, most of the time, in that situation at least, I can write down what this kappa is in closed form. And now this objective, you know, here's where, okay, so let's take this this part here. This thing right here can be written as a sum over j, and now we can expand this out so we can do k1 and k2, sum of two k's, alpha k1 times alpha k2, z k1 j, z k2 j. And we can again switch the j to bring that sum over j in as far as we can, and we end up getting that this is equal to the sum over k1 k2 with alpha k1 times alpha k2 times, we have this zk1 transpose zk2. That's one way that we can write this. So it turns out that this objective can further just be written as a function of this kernel here. Function of this kernel. Because the only places where z appears is as zk1 transpose zk2, or zi transpose zk. Yeah.
The notation means just having two values in the sum, or it's a double sum?
It's a double sum, yeah. So it's, maybe it's more clear if I write it as a sum over k1 and k2. This is equal to that. Okay. So it turns out, you know, you can write all of these in matrix notation, a lot of this stuff in matrix notation, but I kept it as sums to be a bit more clear what's going on. Okay. So every time, so I'll just finish this up. So star, now we can say, well, it's the minimum over alpha of this, which is in Rn, this 1 over n, sum I equals 1 to n. This loss, yi, we still have the sum over k, alpha k, but now we have the kernel. We're just, every time we see a zi transpose zk, we replace it with something. This kernel, xi, xk. The loss, plus our lambda. Now we just replace it with what we have here, sum over k1, k2 of alpha k1, alpha k2, and we have our kernel. Kernel here, x k1 times over x k2. Okay, so the point is that I actually didn't need to form the z's at all. If I have access to this kappa, then I don't need to form the z's in this level. So here's an example of why that's useful. So for example, the dth degree polynomial kernel, this can be written if you have x I and x k here. If we have that, then we're going to write it as 1 plus xi transpose xk to the d. So xi was, in our example before, that was a two-dimensional x. Now it turns out that you can always write this as So for d equals 2, for example, d equals 2. So I've just made up this kernel, right? Well, I didn't make it up, but this is a common kernel that's used. And we could, if you gave me an xi and xk, I could compute it, right? Just give me two-dimensional vectors. I can take their inner product, I can add 1, I can raise it to the d. So if d was 2, which was our example beforehand, then this is just equal to 1 plus xi1 times xk1 plus xi2 times xk2 squared. This is equal to 1 plus 2xi1 times xk1 plus 2 times xi2 xk2, and plus, then we get higher order terms. We get x I1 squared x k1 squared plus x I2 squared x k2 squared plus, then we get our cross terms. It's 2 xi1 xi2 xk1 xk2. This is a little tedious, but so yeah, so this is, if I wrote this kernel in closed form, this is what I would compute, but we can expand it in this way. And the point is that this is actually can be written as an inner product between two 6-dimensional features. And that is 1 root 2 xi1 root 2 xi2 root 2 xi1 x times xi2 xi2 and then xi1 squared and xi2 squared, and then this transpose with the same thing but for xk. Right? So I'm just going to write that as the ellipsis. Because when we take 1 times 1, then we get this 1 term here, root 2 xi, 1 times root 2 xk1, we get it here, and so on. But, so the point was that, we could have expanded it in the spaces, right? And this is the same basis as we had before, except there's these root 2's in a couple of places. Right? But effectively, it's the same thing. So we could have expanded it like this and then done our usual linear method. Or we could have just computed this kernel instead, which is arguably, it may be easier, may not be, depending on D effectively. We could have computed this kernel and then just solved this program here, which is what actually, this is actually what gets solved in a lot of scikit-learn's methods. Okay, so another example. Okay, so part of the idea here is that we actually didn't need. Now we've sort of separated ourselves completely from the idea of feature engineering. Right? We really just needed this kernel. We needed this notion of similarity. So now I can start thinking of notions of similarities. Instead of engineering features, I can think about engineering similarities. Right? And very little is required. Right? It's just a function that takes in our two samples. Right? So this could be two text documents. It could be two images. It could be two of all sorts of objects, and I just need that this notion of similarity satisfies some very, very basic constraints. So, so for example, given any vector, I can define the following kernel, so xi and xk, to be equal to e to the negative xi minus xk. And this is our, I'm going to use our Euclidean distance between xi and xk. That could really be any distance. divided by some notion of bandwidth. So this is a similarity, right? That I could propose, and this is a well-known similarity called the radial basis function. So it's a well-known kernel, the radial basis function, RBF. So now it's sort of like philosophically we switched. We switched from going from feature engineering to similarity engineering, and we have the direction and we have the logic in one way, right? We say if we construct feature engineers, or if we're doing feature engineering, we're constructing new features, then that's equivalent to this idea of constructing a notion of similarity, that's the derivation we went through, right? That notion of similarity is the features inner product with each other. It turns out that you can go backwards. So this is a mathematical theorem is required for this pretty deep mathematical theorem. But yeah.
What do you mean by similarity? Similarity.
So the kernel is a notion of similarity. If it's large, then the two samples are thought to be very similar.
Because you think of it as a dot product.
Yeah. It effectively is forming a type. It's forming an inner product. That's right. Yeah, it's forming an inner product. But
and you can have cross terms too. So.
Yeah. You can. So like if you think of the radial basis function, if x1 if xi is exactly equal to xk, then this is 0 and this is 1. And for any pair xi xk, it's less than or equal to 1. So it's sort of like the radial basis function is largest at 1, and that's when they're exactly overlapping. But this is really a very general thing. So so if we were to compare a list of documents, we could just say, do they contain any of the same words? That could be our notion of similarity. And then it might be much easier to just compute this similarity explicitly for every pair of documents and then run the algorithm. Right? If we were trying to predict something else, like whether the documents were about the topic. Okay. So this is another one. It turns out that the radial basis function can be written as the inner product between two feature vectors, but they're actually infinite dimensional feature vectors. So there's infinitely many components. So this is a very extreme case of feature engineering, right? We're thinking of infinitely many features that are constructed, but it turns out that there's nothing keeping us from being able to compute this kernel, the RBF kernel, between every pair. So that's a case where it would be impossible to construct the full set of features because there's infinite of them. Okay, so going back to this, so a couple of issues with this is that when we have something like the radial basis function, this bandwidth parameter here, let me describe why. Actually, I'll jump back to the bandwidth in a minute. Okay, so let's go back to the polynomial basis example. I had these, so before I had no noise in the y's, right? No noise in the labels. They were determined completely by this polynomial separator. Now I'm going to add noise to it. So it's the same polynomial separator that we had before, except now I have noisy observations. What I'm going to do is okay, so we could, in this case, for these actual labels, we could engineer the features with just the quadratic monomials, right? So what we had before. And then we could compute, for example, this ROC curve that we talked about last time. So this was this true positive rate against the false positive rate. And remember, with the RSC curve, we want it to be in this top left-hand corner. So this is doing relatively well. It's, for example, saying that for a false positive rate of around 0.1, we can get a true positive rate around 0.8, a little over 0.8. So that's pretty decent. I mean, of course, decent depends on the level of noise that you have. Now, suppose we wanted to instead construct features for different degree monomials. Right? So just think about the dth degree polynomial kernel that we had before. I chose d equals 2, and that corresponds to this set of features that I've constructed here. I could have chosen d to be higher. Right? I could have created higher degree monomials. So I'm going to allow that degree to vary. And then I'm going to just look at the 0-1 loss, right? So how many misclassified points do I have as that degree varies? So one thing that happens is that if we look at our, sort of made this up just now, so you don't see an extreme amount of overfitting in this situation. But what tends to happen is that if you look at your training error, which is the data set that we trained on, right? Then you get that the number of misclassified points is generally just going to decrease. But the issue is that when you start constructing features, every feature is going to help your training error. And the idea is that we've constructed our beta. So our support vector machines and all of these, they're designed to minimize your empirical risk, right? The risk over the training set. Right? So, of course, if you were to use that same training risk to evaluate your performance, then that's going to be a relatively low error. But then what happens is that if you were to, say, get more data, and then evaluate your performance on that new data, we're going to call that our test error. Right? So our new data, we have whatever came out of our training set, whatever classifier we got, we just evaluated on this test error. So typically what's going to happen is that the test error is going to be a relatively faithful, representation, non-biased representation of this notion of true risk. So what's the probability that I correctly classify my point when I get a new point? Because it's sort of a simulation of that. Whereas the training error is not going to be a faithful representation. So the training error is always going to be less than the test error. What we see here is actually, this can happen quite often, is that actually as we increase our degree, the test error doesn't get that significantly worse. But it always is going to be larger than our training error, which is also what we see. So if I were to output my training error and say this is the error that I'm getting, then that won't be honest in the sense that I know that there's going to be some bias because I've used it to construct my classifier. But if I do output my test error, then that should be unbiased. Now, typically what we do is we use this to tune something like this choice of degree. This degree, we can either think of it as determining the features that we engineer, because each degree gives us a different set of features, an increasing set of features, or we can think of it as tuning the kernel itself. Because in the d degree polynomial kernel, we used it. So it didn't impact the test error all that much here. So I got this is a widely distributed data set. It's this blood transfusion data set. You can find it, I think, on the ECI machine learning repository. So it's sort of a commonly used data set. The idea is that they perform these blood transfusions and then Yeah, they tried to predict. They tried to predict whether people are in support of this donating blood or not, based on several variables that they extracted from the survey. What I did in this case is I used they have several variables, 4 variables, and I used the RBF kernel, this radial basis function kernel, and we're just going to look at that. And then I plotted the test error versus the log of that bandwidth parameter. And so the test error, and this is sort of the typical thing that we see, is that there's some bandwidth that's just right. And the test error, it starts out being relatively high. And so this is not a percentage, this is the total number of misclassified points on the y-axis. And then it'll decrease, it'll bottom out at some point, and then as we increase the log bandwidth, it'll increase again. So this is sort of a typical thing that we should expect to see. And the reason that we see this sort of thing is that when the bandwidth is very small, then we're going to say that we have a relatively low bias for our classifier. And then if it's very large, we're going to say that it has a high bias. And if it's very small, then there's a high variance for the classifier, and it's very large, then we have a low variance. And I'll try to illustrate what I mean by that. Okay, so let's look at this radial basis function. So if I were to say our data points look like this. So this is our x points. And here is, for example, a new data point that I'm going to classify. Call it x star. This is our new data point. So if I have a very large bandwidth, let's make a circle around this new point. And let's say this circle represents the circle of radius 3 times sigma, root 3 times sigma squared. Or sorry, just root 3 times sigma. So this is the circle of that radius. Then the idea is that if I look at the kernel, which is telling me how xk is influencing xi, right? If I look at this kernel, any point that's outside of this circle here is going to have a kernel that's smaller than e to the minus 3, which is a pretty small number. Anything inside of this circle is going to have a kernel that's larger than that. And so if I were to reduce this bandwidth, then what ends up happening is that I'm using fewer points effectively when in my classifier. And if I increase this, then I'm using more points. And so it should make sense that if we were to use sigma large, then we're using more points. We're effectively using more points for predicting this point x star. And so with sigma large, then we have a high bias. And this is because we're using a lot of points that are pretty far away from this x star, right? Which might not be representative of the distribution of x star because they're so far away. But because we're using so many points, we might get a very low variance. This is a high bias, low variance. Where if sigma is small, then we might get a low bias. And the idea is that if sigma is small, we're using only points that are close by to x star, effectively. But then it's going to be a high variance. It's going to have a higher variance. And that's because we're using fewer points to predict. Right? Effectively, we're using fewer points to predict, so we get this higher variance. So that's the basic idea behind the selection of the bandwidth, is that you get these two things. And so when you look at your training error or your test error, it's some combination of bias and variance, right? If the bias is very high, then you're going to have a poor test error just because an expectation you're going to do poorly. Right? If you have a high variance, then your test error is going to be high just because your predictor is unstable. So that's the intuition.
So is this going to perform better than Kernel Trick, or the performance is the same?
Yeah. So K-nearest neighbor has an advantage, and that's because K-nearest neighbor has this tendency to zoom in on regions where you have lots of exploits, lots of data. So in some sense, it's sort of like an adaptive kernel, or an adaptive bandwidth, because the bandwidth has this tendency to adapt to where you have more data points. But a couple of disadvantages with KNN. The main disadvantage with KNN is that it's very slow to do the prediction task of KNN. Right? Because with KNN, you have to find what the nearest neighbors are. And that's extremely slow. You effectively have to construct, specific data structures that are designed to make it so that it's easy to find nearest neighbors. But in my opinion, that's the big disadvantage of KNN, is that it involves these sorting procedures, and the prediction task is very hard. So I tried to, so this was a bit of an experiment to see how much I could get through with as little math and details as possible. If there are questions left over, which undoubtedly there should be, you can feel free to ask me, and I'll explain something in more detail. But yeah. Thank you. Yeah, thanks, guys. That was fun. I'm fine. Hey, yeah, I don't know. You know, I have no idea what the level of the audience.
Yeah.
So it's sort of like, it's a little tricky.
I mean, I guess there was some tutoring.
Yeah, I'm not sure, yeah.
The question would be, do you have any further readings or just?
Yeah, so, let me think. So, it depends on the level and then sort of the focus that you want this to be. Most machine learning, intro machine learning textbooks will have this idea of the kernel trick in it. And actually, even there's a deep learning textbook that just came out that has this kernel trick introduced in it, and has a pretty good introduction to these ideas.